right, so I will talk about a relation between Tame geometry and Hodge theory. Well, actually, I want to more generally talk about relation of Tame geometry with other structures. So first of all, let me say a few words about how you do geometry with o-minimality. So yesterday, Gal defined what is an o-minimal structure, and you saw that it was just a collection of sets in Rn for all n satisfying certain properties. So maybe I recall this. So S, an o-minimal structure, just a collection of sets in Rn you're authorized to play with. It has to satisfy some basic properties. It has to be stable and finite intersection, finite union, and complement. It has to be stable under linear projection and products. You want the theory which is not empty, so you ask that you have all the algebraic sets are definable. So this is your definition of a structure. And then the important o-minimal axiom, and the only axiom that is important for doing geometry is that any one-dimensional guy, so here is the dimension, or just one, has finitely many connected component. Which is equivalent to say that A is finite union of points in intervals. Okay, and then Gal explained that this property basically propagates through the entire structure. So any definable set in such a structure will have finitely many connected components. And this is where tameness enters the picture. So now, of course, everything here is inside Rn. So the first thing I want to say a few words about is that you want to have a global notion. Usually in geometry, you don't want to refer to everything being embedded in Rn. So the way you do that is you just copy the usual definitions of manifolds, topological spaces, but adding one axiom, which is that the covering by opens has to be finite, so that you keep the finiteness that you have in this structure. Okay, so you get the notion of o-minimal topological space or manifold. So you have to be careful that usually you of course you can define C infinity, but it's usually better to think that everything is at finite order, again, because you want to keep this finiteness property. So for instance, let me give a more formal definition so that we are sure that we are talking about the same thing. So what will be an o-minimal CR manifold? So I will fix an o-minimal structure S in the rest of the talk. I will just say definable for S definable, okay? So M definable CR manifolds just means, for instance, that you can write M as being, first of all, a manifold in CR manifold in the usual sense. But now you ask that M can be written as a finite union, really finite. So this is where I want to insist on this, of opens. So, and now these guys have charts inside Rn. And now what are you asking? Well, you want those VIs to be definable, okay, inside Rn, such that for any I and j, actually what you want that the intersection 2 by 2 of those Vij are definable. Let's say phi j of ui intersected with uj is definable. So I'm writing it like this, but when j is equal to I, in particular, you're asking that vi is definable, but not only them, but the intersection 2 by 2. And now you ask that the change of coordinates are also definable. So if I look at phi ij, which by definition is phi j minus 1 phi I applied to ui intersected, let's write it this way, from vij, so this guy by definition is that one, so I do not repeat, to vji is definable. So this is right. So usual definition of a manifold, but you are just asking that the change of coordinates are definable in your structure and that you have finitely many charts. Okay. So this defines the objects, and then of course you can define a map between manifolds being definable. So what are the morphisms? If you have two manifolds n and prime, what will be a definable morphism? Well, it's just a morphism that becomes definable when you read them in charts, such that f read in charts is definable. So this means you pick a chart here, you take the preimage by f, you intersect with another chart. First of all, you want this intersection to be definable, and then the morphism written in those charts is definable. So everything is read in Rn, but okay, does it make sense, or am I going too fast?
No, it's good, but maybe you have to say what you mean that a function is definable, because S is a collection of sets, and you talk about a definable function. That's the graph. You take the graph.
Yeah, sure. Yeah. Yesterday it was also mentioned by Gal. So, well, when you define minimal structures, as everything in mathematics, usually you have a dual point of view. Either you define the sets, and then the functions which are admissible are the ones are definable, are the ones whose graph is definable, or you start with the functions, and then the sets that you introduce are the source, the target, and whatever you need to make a sense in this theory. Okay.
I'm very unfamiliar with the subject, but is notion of definable related in any way to notion of computable? The computer scientists are talking about?
Well, this is what Gal explained yesterday, is that for me, I will not be talking about any kind of sharp o-minimality where you try to put more inputs in computing the complexity of such things. So Gal explained yesterday, you can put a format and a degree associated to this kind of thing, and certain o-minimal structures have this feature where you can effectively bound the complexity in some sense. So, okay, so this is very formal, this definition. What you have to understand is that there are two components in this definition. The first one is it's a local properties, because you are defining which kind of local functions I'm allowed to use. If I'm in R-alg, I'm allowed only real algebraic, semi-algebraic functions. If I'm in Rn, I'm allowing any kind of analytic function restricted to compact sets. If I'm in Rx, I can use the full exponential. So this is the local properties. But you have to understand that because you have this finite cover, you are also saying a lot about what happens at infinity in that space. Because you are really describing how you go to infinity in one chart. Okay. So those two features are the important ones for doing geometry. So now I will say a few words about things which are not at all developed in some sense and are waiting for some interested people to do it. Is that in some sense you can upgrade the entire program in differential geometry, Riemann geometry, symplectic geometry, whatever. You can do it in Tame world. So let's say differential geometry in general. So what are the classical objects that you want to consider in geometry? Well, there is a notion of bundle. So you can define what is a Tame bundle. It will just be a bundle which is living over such a definable manifold, so locally trivialized in some finite definable cover, and such that the gluing morphisms are also definable functions. So you put definable everywhere, and you have to understand exactly what it means, but this is what you do. So you have a notion of definable bundle. So a typical example is M is at least C1 manifold. If M is definable, then it implies that its tangent bundle or its cotangent bundle or any tensor power is a definable bundle. Right? For instance, for the tangent bundle, it just means that the change of coordinates are given by the differential of those functions, but those differentials are also definable. So this means that for physicists, of course, it is important to get a notion of definable connection bundles. So we can define what is a definable Riemann metric. On a definable manifold, because what is a metric? Well, basically, this is a section of the second symmetric power T star M. So if M is definable, this bundle is definable. And what you want is that this section is a definable section. Of course, there is a positivity condition that you have to put so that is positive definite, but definable, so metric such that G is a definable section. Does it make sense or, yeah? So, and something which is pretty interesting is that if you look at the usual guys that you study in differential geometry course, they're actually the metrics, for instance, in hyperbolic space or whatever, they are all definable. Actually, one of the basic things that we should have noticed is that the Euclidean distance, it's semi-algebraic, right? It's square root of x1 square plus xn square. So this is a semi-algebraic function. And this is why, in some sense, Tame geometry in Rn is so nice. It just, if you want to prove that the closure, topological closure of a subset of a definable set is definable, actually, you are using that for, you are looking at, for any epsilon, I want a point sufficiently close from my set. But this distance is a definable semi-algebraic functions. And so this is what implies, in some sense, once you eliminate all the quantifiers using definability, that the closure of something definable is definable.
But Bruno, that is a bit circular because
yeah, of course. I completely agree.
Make
All right, so you can do that. You can do definable simplex. I'm just saying that nobody really tried to understand what are the important features of those definable Riemann metric or definable symplectic geometry or whatever. It's completely open. So if you want to think about this, so you can do definable symplectic geometry, and of course you can do a definable complex geometry. And this is the thing I'm going to. So there are many ways of defining this. If you think of a complex structure as being an operator that acts on the tangent bundle so that you can decompose it into, once you complexify into holomorphic part and anti-holomorphic, you ask this operator to be definable in the sense I just define similarly to a metric. Okay? And otherwise, you can just think that you're identifying C with R2, and you are looking at finitely many shards in C to the n, so in R to the 2n, and you ask that the change of coordinates are once holomorphic, when I think of this as change of coordinates in C to the n, and second, definable if I think of them as change of coordinates in R to the 2n. All right, so, but before going to that, I want to make some philosophical remarks. Okay. Maybe not so philosophical, actually. So when you do geometry, you have the feeling that everything is pretty nice, but then you try to compare it to algebraic topology. And then you realize that in algebraic topology, most of the objects that you define are not compatible with any kind of geometric structure. For instance, if you think about how you define, so yeah, maybe I want let me first make the remark about what is super special about Tame geometry. So there is one big exception about everything that you can do usually is just the following fundamental fact. So one big exception. And actually, I think this is really the source of most of the richness of the theory is that if M is definable, so you fix a definable structure, and then you do the basic things that any algebraic geometer will often do, or a differential geometer for that matter. You look at the universal cover. Then the universal cover, which is this, has no induced o-minimal structure, definable structure, as soon as the fundamental group is infinite. Right? Why? Because if you have these guys and this is an infinite cover, if the fundamental group is infinite, so of course locally the structure is exactly the same. But this map is highly periodic. It has a periodic group which is infinite. So this map can never be definable for that reason, because the fiber should be definable too if the morphism was definable, but then it should be finite because it's discrete. And that's one of the big change in the game. Because if you start with the Riemannian geometry, of course, the universal cover, you can pull back the metric, it's Riemannian. Same thing for symplectic. So from that point of view, you see that this is super similar to what happens in complex algebraic geometry. In complex algebraic geometry, as soon as the pi1 is infinite, the universal cover usually has no algebraic structure at all. Okay? So similar to what happens in complex algebraic geometry. So the universal cover has a nice complex analytic structure, but usually no algebraic structure. So it's a bit parallel. And what I'm saying is that you have to think that this is one level of complexity added to what happens in usual algebraic topology. I mean, in algebraic topology, people are not frightened to work with very big spaces. Once they have the universal covers, and we construct Postnikov towers where you can actually look at all the higher homotopy groups, but those guys become enormous topological spaces who have no geometric structure at all. It's just that here it happens at the first step. When you look already at the universal cover, you already have problems. Okay, so, and we'll see that in some sense, playing between this guy and this guy, this is the main game that we look at today. So actually, this is one of the force of the theory, because there is a particular, so yeah. A second remark after this one big exception is that usually a given manifold M can have a lot of non-equivalent definable structures. And in good cases, actually, you can construct them using the universal cover. So if M tilde is infinite, and M tilde has a natural o-minimal structure, then actually you can construct, you can use that to construct a lot of o-minimal structures on M. So this is what I want to explain. I think I will just give an example to illustrate this. As a natural o-minimal structure, which is equivariant under the action of pi1, right? So this means that if you take an element in the fundamental group, it is acting on the universal cover, and you're asking that it is preserving this o-minimal structure on the universal cover, then actually you can use this to construct an o-minimal structure on the quotient. How do you do that? Well, it's enough to describe a fundamental domain in M tilde for the action of that group that will be actually a definable fundamental domain. And then you decide that the structure on the quotient is the one given by this fundamental domain. Okay. So let me explain this on one example. So let's take a super simple example, and because after that I will move to complex geometry. Let's take M being C star. Okay, so this is just C minus 0, and I can just think as this guy as being R2 minus 0. So it has a natural o-minimal structure, which is just, I consider this, so this is obviously definable in our alge, and I'm removing a single point, so this is naturally definable in our alge, and the first structure that I will put on it is the first definable structure. It just considering this as being the multiplicative group of a C with this definable structure, identifying it with R2 minus 0. Okay, so that's one. Now let's try to, and this, in some sense, this is the one which is God given. But now let's use the universal cover. So this guy is not simply connected. It has a fundamental group, which is just Z. So we can look at the universal cover. And what is the universal cover? Well, it happens in this case that the universal cover is just C. So it's also R2, so it has a natural o-minimal structure. Okay? So it's just a map that to Z associates exponential 2 pi I Z. So it's periodic of P at Z, and so the pi 1 is Z. You identify this guy with C mod Z. Okay. All right. So now suppose I want to construct a definable structure here. How do I do that? Well, what I will do, I will fix a fundamental domain for that action, which is definable for the natural o-minimal structure, I mean, the natural real algebraic structure on this thing. And if I do that, then I can transport the structure on the fundamental domain to the quotient. It might be an o-minimal structure on the quotient. But now I have a lot of choices because this fundamental domain has absolutely nothing canonical. I can choose it as I want. So let me consider the following example. So what you can do, for instance, is that you can look at those slanted strips. So you fix a line, so this is 0 in R2, and I fix a real number A, let's say, and I look at the strip, which is the following one. So here is 1. I take the parallel, and I look at that strip. So technically speaking, FA will be that guy, and so this is the set of Z in C such that A, imaginary part of Z, is smaller than the real part of Z, is smaller than 1 plus A, imaginary part of Z. Okay. So I claim this guy is fundamental set for this action. So what is the action here? It's basically just translating by 1. So I will cover the entire plane, and it's, well, if I remove this line, I take the open thing, this is 1-to-1 onto the quotient. Now you have to understand a bit what this map is doing if you take this exponential, apply to that thing. So I'm very bad with pictures. I'm not like Delis. So let me try to make the picture. So what happens is basically you will send this line here, you will send it to some kind of spiral like this. And you have to imagine that you continue to infinity, increasing the radius more and more. This is what happens for this map. And so this means, and of course, this point is excluded now. This is the 0 that you are removing C star. And so you have to think that that one so you are mapped to something like this, and this is the image of this band, basically in C star. But of course, it will cover everything because it's turning around. Okay, so here I'm not putting the full fundamental domain. Otherwise, I would cover everything. You have to think that I'm making an image of that band. Yeah, a smaller one. Okay. Of course, if I take this one going to infinity, then actually I cover everything. So this is what happens, and. So I've put a new definable structure on C star, just identifying this guy with this band here, okay? And clearly this put a real semi-algebraic structure because this thing, the equations are just linear. So I mean, it's a semi-algebraic fundamental domain. So so this defines, let's call it C star A. Depending on that parameter, I get a real semi-algebraic structure on C star. and for any a real guy. So of course, you can argue that if you look at the case A is equal to 0, this is a standard one, if you want to call it standard. This is the one where the band is just vertical between 0 and 1. And you are just taking the most, in some sense, the most natural, but it does not mean anything. It's just a matter of taste. Okay.
The question before you erase it. So you made it. Are you making a general statement? You said if you have a cover and you have a structure on.
Yeah, I'm making.
Cover, then are you assuming that this equivalent action is definable?
Yeah. So this is what I said as a natural, which is equivalent to pi 1. I just.
Yeah, it's equivalent, but are you assuming that the action is defined?
With a definable action.
So this.
Yes, this is important. Otherwise, the thing has become much more tricky. All right, so you see that you get all those o-minimal structures, semi-real algebraic structures on C star. And so the way it is defined is that basically you are just identifying by E with this guy. And so this means that if you want to see if something for this structure is definable, you just have to put it back into this fundamental domain under that map and look if it here, this is definable or not. Okay. All right, so there are a few claims. So the first is that all the CAs that you define this way are actually are Hodge isomorphic. So which means that I can construct an isomorphism of Hodge manifolds between those two guys for two different values of A. So it's enough to show that they are all equivalent to F0. So what I'm saying is that basically I just have to tell you that this guy is identical as a semi-algebraic set to that guy, which is obvious. I mean, there is an obvious transformation just because you can identify F0 with Fa by the following clearly semi-algebraic map, which is x plus Iy. So I'm thinking that I'm inside R2, so I have the two coordinates, and it's just mapped to x plus Ay plus Iy. And this map is clearly, it's even better than semi-algebraic, it's linear. Okay. All right, so that's the first thing. So now you can ask, let's try to compare this one with the previous one that I had that I erased, which was GM. Well, the claim is that now if I look at the identity map from CA star to GM, this is not definable. For any A non-zero in any o-minimal structure. So not only they are not identical as semi-algebraic structure, but they are not identical if I take any extension of R-alge. For any A, if A is different from 0 in any o-minimal structure. And so what is the proof? Well, in the usual GMC, if I take a ray originating from 0, then it is semi-algebraic, it's linear for the natural structure in R2 minus 0. So now if I take a ray and I look at its frame image under that map here, well, you see immediately that you will get infinitely many connected components because you will look at where this ray, so you will get one component here, but then you have to understand that you are continuing turning, so you will continue to cut farther away this ray. So which means that here, you will map that ray at many places, in infinitely many connected components, and that's a proof. This guy is definable, but when I read it in some other structure, it has infinitely many connected components, so it has no chance to be definable. And so this proves that this is not an ISO. Is it clear? Yeah. All right, so that's one thing. But now let's look at the interesting case that I did not cover here, which was the case A is equal to 0. If you think about it, I just tricked you because this is true only if this map is like that, as some slope. So now let's look at the interesting case is the case, look at the identity map here. This map is still not are Hodge definable. Why? Well, let's look at this picture now. So now I'm in the case where the map is vertical. So I'm looking at this band. And so now what is this map in coordinates? This map, I'm just identifying, so I'm identifying this guy with F0. And what is that map? Like this. Well, I'm just taking xy, so real part and imaginary part. I'm just writing the exponential in those coordinates. So what you get exponential minus 2 pi I times cos 2 pi x, and exponential minus 2 pi I sine 2 pi x. And those coordinates are the natural definable coordinates in R2 minus 0. But obviously, this is not the real algebraic map because there is this exponential. Okay. So this is not R-Alge, this is not even Rn. For the same reason, because you need the full graph of the exponential, because y is going to from minus infinity to plus infinity. So you need the full graph of the exponential, which is not defined in Rn. But now this thing becomes definable in Rnx. But this is an isomorphism in Rnx. And the reason is that, okay, this function is definable because I have x, the real exponential occur in my structure. And those guys, they seem very non-definable because they are oscillating. But now you have to think that x is between 0 and 1. So, okay, it's oscillating there, but it's a real analytic function with some compact, so it's in Rn. And so this is well defined. And of course, this is an isomorphism, so you're fine. Okay. So you see that the situation is pretty tricky, and that you can use the universal cover to actually define some definable structure downstairs, and you can vary them. So it's and there is nothing canonical. You really have to choose depending on what you want to do. All right. So yeah.
You show that identity is not definable, but how do you know there's not some other isomorphism that?
Yeah, I'm just okay. I should I should state it more carefully. I just proved here that the identity is not. You're right that if you want to prove
It is true that there's infinity.
it's true that it's still true that there is none. Yeah.
So but then it's kind of confusing because in one, aren't you saying they're all isomorphic? And
Yeah, in one, they are all isomorphic, and this is exactly what I'm saying. Is that so? This is his remark. Is that if you use this isomorphism and you compose it, but it's not the identity. Okay, so.
So the identity is not.
The identity is never. These are all different if you consider the identity.
If I consider the identity, they are all different here. Okay. So I'm just trying to emphasize that the situation is pretty complicated depending on which map you allow yourself to consider. The identity map, I mean, it's not definable here. I have to do this map, which is not the identity once I apply the exponential. Okay. So this answers your question and says that I was treacherous even more than what you thought.
Okay, but is it true that there are infinitely many non-isomorphic?
So here,
On C star.
on C star, yes. Alge, yes. I'm not defining all of them. I could take. Okay. I was just taking very simple definable domain. I could take even more complicated.
Yeah.
Okay. I'm just using slanted strips. I could use any kind of fundamental domain for this action. So I'm just trying to emphasize that there are a lot of choices and you have to be very careful in what you are doing in this kind of business if you want to do geometry. So on the other hand, there is another class of examples where the structure is completely canonical and they come from algebraic geometry. So if you take X, any real algebraic geometry, algebraic variety, then naturally you can look at its sets of real points. So I just mean that this is defined by some polynomial equations with real coefficients. Then, and if you if you put the topological, the usual Euclidean topology, then this thing is naturally R definable. So why is it so? It's just that if you have an algebraic varieties, and by definition, this means that it is covered by finitely many affine varieties. And for affine varieties, this is trivial. I'm inside R to the 2n, and I'm taking some affine varieties there. So it will be given by polynomial equations, in particular semi-algebraic functions. And so this set is actually definable in R alg. Okay. And so this result applies literally to X, also a complex algebraic variety. Just because I can think of it as being a real algebraic variety by taking restriction of scalars and applying the previous result. So and of course, all the algebraic morphisms give you definable semi-algebraic morphism. Okay, so this is the complete opposite. Here in that situation, if I start with an well. All right, so I spent a lot of time on this. So now actually I want to turn. So I want to do something very stupid, apparently, is I just told you that any algebraic variety is naturally definable even in the smallest possible o-minimal structure, which is R alg. So why should I care about o-minimal geometry if I'm doing algebraic geometry? And this is what I want to explain now. And basically, by algebraic geometry here, I really mean complex algebraic geometry. I'm not working on finite fields or anything more fancy like this. So the natural question, as I said, why should I care? Right, because in this world of algebraic geometry, everything is definable by definition. I'm considering only algebraic varieties, which are definable, and algebraic morphisms, which are also definable. And the answer was given basically by Dolin yesterday. And philosophically speaking, it's just that all the important conjectures in algebraic geometry, actually, they are not algebraic. Not all of them. I'm just pushing to what I really want to believe. But let's say, for me, at least, the most interesting questions in algebraic geometry occur at its border, where the things become non-algebraic. So it's really at the interface between algebraic geometry and complex analytic geometry that things are happening. Okay, and even to be even more specific, you have to think that most of the interesting questions, what they actually do is they compare different algebraic structures with transcendental maps. And this is what happens. You really want to understand those transcendental maps that give you isomorphism. And in some sense, Tame geometry is done for that. Okay. So those questions, basically they study transcendental comparison maps between different algebraic structures. So this is really the motto of this thing. And so, and Tame geometry is really a device for that. And Tame geometry can be used here. And not only this, it studies those comparison map, but the important, so if you think about, let me give just, so yesterday, for those who attended Dunning's talk, he introduced the Hodge conjecture. Now we'll come back to that, to Hodge theory in the next part, but really the Hodge conjecture is really something about comparing two kinds of different algebraic structures, the one given by the usual cohomology, Betti cohomology, singular cohomology, it gives you some algebraic structure, and the one coming from algebraic Durham cohomology, which is something more intrinsic to an algebraic variety. So, and there is another famous conjecture, which is of the same format, Grothendieck-Spirit conjecture, and so on and so forth. They are all on this format. You take two different algebraic structures. By some miracle of the theory, you get some isomorphism between them, but the isomorphism is not algebraic. It does not preserve the structure. Okay, so I will come back to that at some point. But really, this is where you care about Tame geometry. And so this is why it is not so surprising that Tame geometry is very efficient in studying Hodge theory. So, and from that point of view, not only you want to have this comparison map, but you want to bound the transcendence of this map. And this is exactly what those conjectures predict. So bound the transcendence of these comparison maps. And this is where you hope that Tame geometry is helping. So now I want to emphasize this. So Gal yesterday already explained one of these kind of theorems that you can use. So now from the perspective of the algebraic geometer, you can think that Tame geometry is telling you how to algebraize a certain number of things. So it's also putting some constraints on definable sets.
Question just to make sure I'm not confused. So, I mean, we have these algebraic varieties and so on. I'm assuming those are part of the Tame geometry.
Yeah, they are, this is what I wrote before. They're automatically definable,
But
even
the
in
ones
our
who are
algebra.
not, the ones, the varieties which are not algebraic are
Yes.
not o-minimal.
So this is where subtle things happens. If you take a compact, complex analytic space, which is not a Keller manifold or not algebraic, it's not. It is definable. It's always definable in our hand just because it's compact. But nevertheless, we cannot apply anything of Tame geometry. I don't know how to prove any single result about them using Tame geometry.
So you're saying subset of.
Yeah. So what I'm saying is that Tame geometry, from that perspective, it's rather you start with different algebraic structure and you try to compare them transcendentally, and then you control the transcendence.
Simpler subset to say something.
So as I said, this Tame geometry will be used to, in some sense, constrain the transcendence of those maps. So, and to do this, you have very powerful algebraization results. So the first kind, Gal explained already yesterday, this is some kind of Diophantine geometric criterion. And this is the Pila-Wilkie theorem. Let me recall the statement that Gal explained yesterday. So let's give the simplest statement. So you put yourself in Rn, okay? And you suppose that this guy is definable, by which I mean, I repeat, that definable in some o-minimal structure, whatever the o-minimal structure, you don't really care at that level. Then you try to detect if that guy contains a lot of semi-algebraic sets. So you call the alg the semi-algebraic part. So this is by definition the union of all positive dimensional semi-algebraic sets contained in Z. So the union of all semi-algebraic curves. Of course, I have to put positive dimensional because points are always semi-algebraic. So if I would not put the positive dimension, this would be everything. So, and now the statement is that, well, as soon as this part is empty, then there are very few rational points. So for any epsilon larger than 0, there is this constant C epsilon, such that if you count the set of points in Z intersected with Q to the N, and now you want to count, so you bound the complexity of those points, so such that the height is smaller than some given number that I denoted by T, I think, like everybody. So you count these things, and now you take them not in Z, but in Z minus Z alg. So if you don't have any semi-algebraic part, there are very few such points. So this number is smaller than C epsilon. It grows more slowly than any polynomial. Subpolynomial, okay? So just to make a picture, suppose you take the box 0, 1 cross 0, 1, and you draw your preferred real analytic curve. So now it's in a box. So this part here is definable because I'm in Rn. It's real analytic in some compact. And I just count the points here, which are in Q square, depending on the height. So if this thing C has a lot, and this is quantified here, at least polynomial in the height, points, rational points, then actually it is algebraic, which is super strong. I mean, just the simplest instance of this theorem. So this is Diophantine geometry reversed. Usually in Diophantine geometry, you start with some algebraic variety defined over Q, and you try to count the points. Here you do the converse. You just take something in Rn and you intersect it with Q to the n, and you count, and you can deduce sometimes that you're algebraic. Okay, so that's one. And now, because I want to move to complex algebraic geometry, the second thing that you can do is to try to study the interaction of Tame geometry with complex analysis. And so there are two mottos. The first motto is that nobody teach anymore complex analysis just because it's too hard. That's true. I mean, I have very bad memories of, especially in higher dimension. In dimension one, it's super nice to some extent. In higher dimension, you don't understand anything. It's really tough. Because there are a lot of pathologies. So actually, I mean, this is a truth of historical development. Grothendieck developed algebraic geometry, and in parallel, the German school developed complex analytic spaces, and the theory Grauert, essentially, and Stein, and so on. And this is much harder. Okay, it's so hard that nobody does it anymore. But the point is, the motto is that if you think of C as being R square, and you try to compare complex analysis and put it with Tame geometry, then essentially you kill all the pathologies of complex analysis. So the pathologies of complex analysis are not compatible with Tame geometry, with real Tame geometry. So this is a motto, and let me try to illustrate this. So already in dimension one, so how to illustrate this? The following, just look at the easiest thing you can do in complex analysis. You take a function on a punctured disk. So this is a disk of radius 1. I remove the origin. I take any holomorphic function, put it f, and it is holomorphic. So the behavior at 0 can be really bad. It can have an essential singularity, right? When you try to develop it into powers, then you will get negative powers going arbitrary negative order. But now suppose that it is also definable, where here I'm just identifying C with R square, and this guy is obviously definable. It's given by this Euclidean, I mean, this semi-algebraic function, all the points of distance to 0 smaller than 1, and I remove 1 point, so this is obviously semi-algebraic, okay? And then the claim, so the lemma is that this thing is, it kills the essential singularity. This map has to be meromorphic, so it's essentially algebraic. And then 0 is not an essential singularity. It is meromorphic. So now the poles have finite order. Okay, and well, let me indicate the proof in case you want to see it. Of course, I would give a proof where I use a big hammer, but nevertheless. So let's look at the graph of this function. So now you're in C square, you take the graph. So let's call it gamma of that graph. And it's just a holomorphic function, and it's defined over this thing. So I take the closure, the topological closure of this, and I remove gamma of f. And then there is, so suppose you have an essential singularity. Then you have a theorem that describes you the closure of that set. It's called the big Picard theorem. It tells you that this thing contains actually the entire line of a 0. Right? If you have an essential singularity, when you look at the graph and you take all the points which are in the closure, over 0, you will get the full line. Okay? So this is the great Picard theorem. So now let's think about this. Now I'm assuming that this thing is definable. So this means exactly that this graph is definable. But by the basic properties that we emphasized yesterday, the closure is also definable. And so this boundary has to be definable. Okay, so it's a definable set, but now the dimension, the real dimension of this thing, because it contains this thing, and dimension, the real dimension is 2, right? Because this thing is obviously of dimension 2. But then this means that it has the same dimension as the graph. Okay. So now you have a definable set whose boundary has the same dimension as the set itself. Right? This is a contradiction. I mean, Tame geometry is divided such that you have a nice stratification theory. You have this decomposition theorem into cells that Gals mentioned, triangulation. So it cannot be true. So this contradicts the definability. So this map cannot have an essential singularity.
You could also apply great concurrent just on the domain itself.
I could also do that. Yeah, there are a lot of variants, but nevertheless, notice that in the proof, I mean, great Picard is difficult to prove. I mean, it's not.
But you don't.
You don't agree? No, I don't need it.
Yeah.
It's just I wanted to give the fast proof in some sense. I'm not saying that you need it, but the fast proof needs it. All right. So this is what happened in dimension 1, and these results propagate in some sense in all dimensions. So now, from the point of view, you have to think that, in some sense, algebraic geometry is just devised in order that you can compactify anything. This is done for this, right? If you have an algebraic variety, you can always compactify it. In complex analysis, this is completely wrong. And this is the main difference between the two. Thanks. And you have to think that tame geometry, in some sense, because of this cellular decomposition, it's helping you to do that. Okay. So in some sense, if you are looking at complex analytic space, which are also tame, this means that you have somewhere a nice topological compactification, and so you can start doing things. So, so in higher dimension, let me mention things that I want to use later. What do you get? Well, let me mention a famous result in complex analysis. So the kind of things that probably you have never seen the proof, because I said this is not taught anymore. It is the following thing. So you take a complex manifold. You can just take C to the n if you want. Now what you do is that you remove some closed analytic subset of smaller dimension, right? So I'm making a hole in my space, complex analytic hole. And now I suppose that inside this open thing, I have X, which is also complex analytic and irreducible. And basically, I'm asking the same question. What is the topological closure of that thing? And if you think of it, you can just think about, for instance, take the graph of the complex exponential. Okay, this is disgusting, honestly. And you are trying to take some closure. So usually what will happen is that this closure, even as a topological space, it's pretty bad. Okay. So now Remert and Stein gave some conditions such that when you take actually the closure, it's still complex analytic of the same dimension. Okay, and the condition that they found is that if the dimension of X is big compared to the dimension of E, then in some sense the holomorphy enables you to go through the singularity and extend something holomorphically. So if this guy has dimension larger than the dimension of E, then actually the topological closure X bar, which now is something in S, is actually complex analytic of same dimension. Right, so you are really completing your complex analytic set by a bigger one. Okay, so this is the theorem. So now there is a variant of this theorem by Petersen and Starchenko using tame geometry. So now suppose that this complex analytic guy S, the global guy, is also definable in some o-minimal structure. So it's a real geometric condition. It has nothing to do a priori with the complex analytic structure. I don't put more assumptions on this, but I assume that this one is also definable. Okay, then you can erase this condition. So you have to understand that this condition in the Remert-Stein theorem, it's really a tame geometric condition. And what I'm saying is that if from the start I'm assuming that this guy is definable inside the big S, then actually I don't need this redundant condition. I can do it in any dimension. Okay. And a corollary of this is that, well, maybe the most famous result in complex algebraic geometry is that inside the projective space, anything holomorphic is algebraic. Right? This is the Chow theorem, which, if you think about it, is really kind of a wonderful theorem, right? You define something by complex analytic equations, and as a fact, it is defined by complex polynomial equations. So here you get a corollary of this. Maybe I should, no, before doing this, writing the corollary, maybe I should give a fast proof how you do that. Depending on what you, I mean, there is an elementary proof using really all the properties of definable structures, but I mean, some topological properties, but I don't have time for this. So let's use again a hammer. So what is the strategy? The strategy is the following. So locally, this problem, I mean, you can look into finitely many charts because everything is definable. And in those charts, you can think that this guy, S, is an open in C to the n. Right? I'm just removing something analytic in C to the n, and I'm in this situation. And now the fact that X is definable, well, Gal explained yesterday that there is a finite triangulation of this. But this result, if you think about it more carefully, it tells you that for the natural metric in C to the n, the 2k, so this guy is of dimension, complex dimension k, so a real dimension 2k. If I look at the volume of that thing, it is automatically bounded. Okay. Now, there is a very nice result due to Bishop that tells you that if you have a complex analytic guy, whose volume is bounded, when you take his closure, it's still complex analytic. So in other words, if you cannot prolong your complex analytic guy by something complex analytic, it's just because actually close to the boundary, close to E, the volume is becoming infinite. Okay. So Bishop theorem tells you that actually X bar is complex analytic because of this condition. So again, I'm using a non-trivial theorem. You can prove it in completely elementary way, but I don't have the time for this. Okay, that's a proof. And as I said, the nice corollary is the following thing. So this is what usually is referred to as being the o-minimal Chow theorem. So if you are inside C to the n, a complex analytic subvariety is much more wide than just a complex algebraic subvariety. Chow theorem tells you that in Pn this is not true. If you are compact, this is not true. You are automatically algebraic. And then the result is that if you take any complex analytic inside, so S is an algebraic variety. We'll see. I look at it as being a definable complex manifold. So I denote by SDEF. And I suppose that I have a complex analytic subguy, which is also definable. Is subdefinable guy of SDEF, then automatically, so you can think that you can take S is equal to C to the n if you want. Maybe the simplest example. So you take something inside C to the n, which is holomorphic and definable. Then automatically it is algebraic. No, complex algebraic. You prove it is semi-algebraic, but because it is complex analytic, it will be automatically complex algebraic actually. Okay, so in some sense, you are just pushing the and to prove this, you can use this. I mean, one of the original proof, one of the proof of there are a lot of proofs of Chow theorem, but one proof is using Hammerstein.
I have a question about this proof. So you are saying that the set is analytic around these points from E.
Yes. Yes.
So do you know if so it means that there are analytic functions?
Yes.
Do you know if the analytic functions are definable in the same structure? I guess maybe they would be.
That's a good question. Yeah, sure, I think they are.
would not follow from this.
It does not. It does not. It's kind of abstract. Yes. All right. So you see that this you are killing a lot of pathologies, and actually, using this, you can define. There is an old formalism, and then of course it's very similar to the formalism of algebraic geometry or of complex analytic space. So you can write pages and pages of formalism. So you define a good notion of category of definable analytic space. And you have to be very careful when you do that. So you want complex analytic manifold, but the main axiom that you want to put the finiteness of the covers. So what you are actually doing, you are defining some kind of Grothendieck topology. It's not a true topology because you have this finite, it's a very mild Grothendieck topology. But then you also want to define sheaves in this topology, in this Grothendieck topology, and so on and so forth. So you develop the entire formalism. And actually what you can do in this formalism, and this is also important for Hodge theory, is that you can develop a Gaga theorem. So for logicians, this Gaga theorem is geometry algebraic, geometry analytic. So it's a famous result of Serre in algebraic geometry. And of course, it's basically telling you that if you are working over a complex algebraic variety, considering complex covariant analytic sheaves or complex algebraic covariant sheaves, it's the same thing. There is no difference. It's a compact. Yeah. And basically, you want to extend once you have. So this is a sheaf theoretic extension of this Chow theorem. And once you have o-minimal Chow, it's very natural to think that you have some kind of o-minimal Gaga. And let me just write it, although I don't want to say anything about this. You can take a scheme, a C, and suppose that now you can look at a definable functor from the category of complex analytic covariant sheaves to current of X def. For the natural definable structure on the scheme. And then this functor, so you take a complex analytic sheaf and you have this definability functors that gives you a sheaf in this new category. And this is fully faithful, exact. So this looks abstract, but actually this is super powerful. And the image is closed undertaking subquotients. But the main difference is that it's not essentially surjective. So it's not true that any guy here is obtained from such a guy here. So it's not exactly the same thing as the usual minimal Gaga. But okay, it's just a parenthesis. Don't think about this. What I want to mention is that out of this formalism, you get a super nice theorem due to Becker, Brunbarb, and Zimmermann. Which is the following. So suppose you start with a scheme or an algebraic space, whatever. C, algebraic variety or C. I don't know why I put, no need to talk about schemes, just take an algebraic variety. And suppose that I have a definable complex analytic space. And suppose that I give myself a definable map from the definable space associated to my algebraic variety to V. So let's call it phi, and this guy is definable. So it's complex analytic, and it's definable in some o-minimal structure, extending our alg. Then actually, so you know that if you had a proper complex analytic map, then the image is nice. But if the map is not proper, the image can be disgusting. This is the leitmotif of everything in this business. And now what I'm saying is that if phi is definable, then I can remove this properness assumption, and in some way, but I can get a factorization of that map through an algebraic variety. So there exists a canonical factorization where this is a closed definable subvariety here, and Y is algebraic. So in some sense, what it is saying is that the image of that map, if you start it from the definable space associated to something algebraic, has a canonical algebraic structure. Okay. So. which is pretty powerful. Even if this guy has no, it's not induced by V because V has no algebraic structure at all. It's just that you manage to descend the algebraic structure on the source to the image. Okay, so now it's time to come to the title of the talk. But the good thing is that Greg this afternoon will continue talking about Hodge loci. So let's talk a bit about Hodge theory. And the claim is that this is a Tame theory. So, of course, physicists usually knows about Hodge theory just because, at least in string theory, you have to study KBRs. But let me recall a short, it's not a course, it's just some ideas about Hodge theory, the way I see it. So what is Hodge theory about? At least in this setting, is the following thing. You start with a complex algebraic variety in general, but for simplicity, suppose it is smooth and projective, so compact. So you can extend the theory, but it's more complicated. So let's do the simplest case. Then out of this, you have a number of invariants. So what is the first invariant that you get? You can take the associated complex analytic space. It's just a complex analytic manifold, and you can even just think of it as being a reasonable topological space. And then you take its singular cohomology, let's say with Q coefficients. And what is Hodge theory doing for you? It defines a canonical filtration on that space, on the complexified space. So you have a complex filtration. The filtration is not defined over Q. It's really defined only over the complex coefficient. So you get a filtered complex vector space. So let me explain in one word how you do that, so that you see the features that you are actually comparing things which are both algebraic, but not, the algebraicity is not coming from the same source. So you start with this singular cohomology. And as I said, it's even divided over Z. So you get this finite rank Z module. It has nothing to do with the algebraic structure on the X. It's just because you have a reasonable CW complex. Okay, so this is what I mean by the algebraic structure on this thing. It comes only from the natural structure of that functor, which is singular cohomology. It has nothing to do with the algebraic structure on X. Okay, so now you do a lot of sequence of isomorphism, and none of them is algebraic in the following sense. First of all, you compare this with the RAM cohomology of forms, right? I mean, the complex singular cohomology, it's canonical isomorphic to the cohomology of the differential forms on the manifold. So you use just the manifold structure, not the algebraic structure again. So, right, so you look at smooth C-infinity forms and you take the Durham complex and you know that you can identify those things. All right, so now you use a bit of shift theory. So you, and this is where the algebra starts, you identify this with the hypercohomology of the analytic Durham complex. So we think that this is the cohomology of this complex analytic manifold. So here I'm just using the complex structure. It's true in full generality. It's a sheaf theoretic statement. Just this sheaf, this constant sheaf, is quasi-isomorphic to this complex. Okay, so and now there is a big step. So some form of Gerger theorem tells you that actually this analytic object can be algebraized. It's the same thing as the hypercohomology for X seen as a scheme of a C now with the algebraic Durham complex. Okay. And now there is no natural relation between that thing and that thing and that thing, but nevertheless, if you follow this sequence of isomorphism, you get an isomorphism like this. Okay. So you have to think that to compare this with this, in the background there is integration, which is a non-algebraic procedure. Okay, and then there is all those things, but at the end of the day, you get this canonical isomorphism. But in the background, you have to think that you're really comparing two completely different things. Here, the structure comes really from the fact that X is an algebraic variety of a C, and here it just comes from the structure of any topological. Ah, he wants to attend. Wow, this guy is dangerous. All right, so you get your complex vector space, and now how do you get the filtration? Well, the filtration just comes from the fact that this guy is filtered. So if you have a filtered complex, it induces a filtration on the cohomology. So we get Fp on that guy, by definition, would just be the image of the cohomology of the truncated complex. So you just cut the complex. It's a complex in positive degree. I just keep the complex starting at degree P. Okay. So I can map this complex to that complex. So it gives me a map from this cohomology to that thing. And you get a vector subspace here coming from the algebraic structure. And this is how you define and transporting this filtration here, you get the Hodge filtration. So you see that there is nothing canonically algebraic in this construction. It's pretty complicated. All right, so
just one question, the general scheme of this Hodge theory. You mentioned Calabi-Yau, why
yes,
business would be familiar with this a little bit. But in physics, C1 is 0 special. But for
yes,
you guys, C1 positive, 0 negative, do they have particular, does C1 negative have bad properties or
no?
Does
From far away, I mean, what is nice about Calabi-Yau is that in some sense, the Hodge filtration is simpler because you have the top part is just dimension 1, so you can start looking at sections there. I mean, you have the canonical N0 form that you can integrate with, I mean, pair with its dual to get a volume form and so on. So you get, in addition, some kind of metrics. But abstractly speaking, it does not make any difference. Actually, if you think about it, abstractly from Hodge theory, and maybe Greg will come back to that, Calabi-Yau is the first non-trivial case, where you have non-trivial period maps which are not algebraic. Let me come to that now. All right, and so so this is a format. You get this filtration, and so now you get Hodge classes. So what are Hodge classes? Well, in some sense, the Hodge classes are exactly the guy that are bialgebraic on both sides, meaning that they come from this algebraic structure here of a Q. So let me put a Q here. And they come from the filtration. And so they are exactly the guys, so the Hodge classes of X are by definition the guys which are on that side on the FP filtration and on the other side in H2PB. They are the guys, and in some sense you have to think that those classes are just trying to control this isomorphism. Okay. So this is seen inside H2P Xn. Let's see. Okay. So now what is the relation with algebraic geometry that Tony was talking about yesterday? Is that if you take an algebraic cycle, so a formal linear combination of codimension P algebraic subvarieties, then you can naturally map this. You have a cycle class, you look at the cohomology class associated to those things. The cycle class will map you to HP. Okay, so it's another way of saying that the algebraic structure on X is trying to control what this isomorphism comparison is doing. It is controlled by some algebraic cycles. All right, so the next thing is that in some sense already there is some tameness in this, in the sense that this filtered vector space, it's not any vector space. Filtered vector space, it's a really bad category if you think about it. Graded vector spaces are nice. Filtered are bad. But the point is that Hodge theory tells you that you're exactly in this situation where actually you have a bigraded situation. So theorem, which is due to Hodge, and then generalized by Dulin in the non-proper setting, but I did not talk about it, is that if you look at this, so you look at this Betty cohomology, and you look at the Hodge filtration on the complexification, this is much more than just a filtered vector space. This is a polarizable. The Hodge structure, let's put degree I of weight I. So there are a lot of words, but it's super simple. It just means that basically this filtration comes from a bigradation with a lot of nice properties. Just means that if you look at Z tensed by C, this complex vector space, actually you have this filtration, but because you have a real structure underlying it, you also have the conjugate filtration. And the statement is that actually this filtration has the following property, is that this is the direct sum of, so this is where the weight plays a role. You can decompose that space like this. And this is equivalent to saying that this is the sum for P plus Q is equal to I of Fp intersected with Fq bar, which is the usual way of writing the Hodge decomposition. But you see that the Hodge decomposition from that point of view, it's a real statement. It's not a complex statement. So it's not holomorphic at all. So that's the first part of the statement. And what is the polarizability? And this is also crucial to not forget this, is that the other piece really controlling this comparison isomorphism is a bilinear form, which is the polarization. So a second is that actually you have a bilinear form coming from the cup pairing on cycles on the algebraic variety, which is defined over Z. So this thing is 1 minus I symmetric. So it is a bilinear symmetric form if I is even and anti-symmetric if I is odd. And it is compatible with the filtration in the sense that Q of Fp and Fi plus 1 minus P equal to 0. That's the first thing. And the second thing is that there is one more real condition, which is absolutely crucial, is that if I change the signs, I look at this decomposition, and if P is even, I keep the same sign of Q restricted to that piece, and otherwise I multiply by -1. And so this is this operator C. So C is this operator which on Fp intersected with Fq bar multiplied by -1 to the P. This Hermitian form is definite positive. Okay. All right, so this is what Hodge theory is telling you, is that basically this Hodge filtration is actually a bigraded filtration if you take into account the real structure. And not only this, but also there is this polarization that gives you some very strong positivity constraints.
Don't we need to take primitive cohomology?
No, I can arrange so that I can reorganize the factor. I'm not saying on the primitive cohomology, it's really coming from the cup pairing, and otherwise I can change, on the non-primitive part, I can change the sign so that I get this.
So in differential forms, the C would be just Hodge star.
Yes. Not the Hodge star, because the Hodge star change the degrees. You just want to change the signs on the harmonic forms.
I have but for the middle.
For the middle cohomology, yes. All right, so now let me, so all this is pretty abstract. I mean, what am I saying is that you have two complex vector space, one coming from the algebraic Durham cohomology, the other one from the singular cohomology. Of course, the isomorphism is algebraic, it's just a linear isomorphism. But what I'm saying is that you have to think that on one side you have a Q structure, and on the other side you have the algebraic structure that comes from the algebraic Durham cohomology. So now you will see this even better if I work family. But now everything becomes functions, and we really see why this is a transcendental theory. So suppose I have a family of Calabi-Yards. Well, let's say any family of smooth projective for this. So a smooth projective family over some base that I denote by S. Then now what I can do is on each fiber is a smooth projective variety. So I get this picture. I have the singular cohomology and a Hodge filtration on the complexified one. And I can look how this filtration moves when I move in the family. Because the morphism is smooth and proper, all the fibers are topologically the same. So I can really move the singular cohomology. It's locally constant. So out of this theory, I get what is called polarizable. So it's a lot of ZVHS. Not only the physicists have the right to use big words. So let me use this word, but what is it? Well, first of all, it's a local system. So this means a flat bundle, which is given just by the family of cohomology of the fibers with Z coefficients. Okay, so it's locally constant when I move the point S in S. I can canonically identify all the fibers. I can follow them flatly. Okay, now I can complexify and put everything in a holomorphic setting. So actually, if I do that, I can take the family of cohomologies coming from the algebraic structure XS over C. So the algebraic de Rham cohomology. So this is also the families of such things in my point. And now this is an algebraic vector bundle. And it is canonically endowed with a filtration. There is a polarization in the background that I will not write. And because this comes from this local system, there is an algebraic flat connection, which is called usually the Gauss-Manin connection. Now, the super important point, and this is what makes this theory works, is that Griffiths discovered that actually what is the compatibility between this connection on this bundle and the fact that there is a filtration. Of course, it does not preserve the filtration, but it moves it just one piece more. So in the Calabi-Yau case, you are in age n0, you just go to age n-1,1 and nothing more. Okay, so this means, abstractly speaking, that you are going to f shifted by -1. So this is called Griffiths transversality. And this is really the key to everything. So this looks like a lot of data, but actually you can incarnate this kind of variation of our structure into what is called a period map. So how does it work? You have your base S. And now you look at this local system. So if you're a local system, the first thing you do is you put it back to the universal cover. So notice that I'm going outside of the algebraic category, because this guy usually, for this local system to be interested, it's an infinite cover. So no algebraic structure there. But now the local system becomes trivial. So this means that all those guys are identified with a single vector space defined over Q. And now I want to parameterize filtration on that vector space, moving with the point S. This is all what I'm doing. I'm just parameterizing filtrations moving depending on the point. So it gives me a map to some flag variety, which is a flag variety parameterizing the kind of filtration I get. So now there are all those conditions coming from the polarization that tell you that this is not any filtration. It has to lie inside some open analytic subspace here, which I'll call, so this is open. And now the second thing is that this comes from a condition of positivity on the bilinear form. But this bilinear form is obviously semi-algebraic. So this is open semi-algebraic. So definable, canonical definable structure there. And now everything is equivariant under the action of pi1. So this means that actually it descends to, there is an action of a discrete group such that you get actually this period map. And here everything is analytic. There is nothing algebraic because this space has no algebraic structure in general. So no algebraic, it's just complex analytic. No algebraic structure in general, except if you are parameterizing families of free varieties or some families of surfaces sometimes, so like K3. But the first case interesting is Calabi-Yau threefold. Then this guy is never algebraic. No algebraic structure. Okay, so you are parameterizing, and this is where I see that you see the difference between the two algebraic structures. What you have done here, you have trivialized one algebraic structure, the one coming from the Betti cohomology, the Q coefficients. And you have parameterized the other structure, which is this algebraic filtration coming from the algebraic structure on the fibers. And it moves analytically, non-algebraically from that perspective. Okay. So, all right, so now what I want to finish, I want to mention this theorem that was mentioned many times yesterday in the physics talk. So, really, let me emphasize, really the transcendence of Hodge theory is the fact that there is no algebraic structure here on this map. If there is an algebraic structure, this map is automatically algebraic, but this is a trivial case of families of abelian varieties. And in most cases, there is no algebraic structure. Okay, so theorem due to Ben Becker, myself, and Jacob Timmerman is the following, is that there are two statements. So the first one is that actually this period map enters the Tame context. So any period domain of this form, D mod gamma, can has a natural RL structure. So it's a definable complex analytic space in the sense that I mentioned before. It's the first thing. And two is that actually any period map by from Sn to d mod gamma is Rnx definable. Okay, so if you think about that, one first corollary of two, well, two is unequal by one because here, of course, I put the natural RH structure I just defined, and I extend it to Rnx. And here, this is the canonical. I should put def. This is the canonical definable structure associated to this algebraic variety. Okay, so the corollary of two plus the result of Becker, Brunbarb, and Zimmerman that mentioned, for instance, tells you the following: that the image is canonically an algebraic structure. So, although this guy has no algebraic structure. Okay, I have to put some mild assumption. You can always assume that this map is proper in order to apply the previous result. So what I want to do, I just want to give an idea of the simplest case of the proof of this so that you really see what happens.
What does natural mean in point?
Sorry?
What does natural mean in point one?
Natural is that, okay, so I will come back and you will use it anyway. So this means that inside this D mod gamma, so this D is associated to the monodromy group. Actually, I should have mentioned this. So you have the local system, so you have an algebraic group associated to this, which is the monodromy group. And this D is homogeneous under the real points of that group. So it's always a semi-simple group. So in the case of Calabi or threefold, for instance, if you have H21 is equal to 1, you get SP4. This is this group, SP4 over R. Okay. So natural means that this is factorial for any subvariety of the form D prime mod gamma prime is naturally definable there, semi-algebraic there, for any natural embedding. So G prime, D prime is contained as a Hodge datum in VD, then D prime mod gamma prime inside D mod gamma is a real semi-algebraic.
But don't you get a semi-algebraic structure depending on each choice of compact maximal subgroup? I mean, you can.
There is a single compact maximal subgroup containing V. This is a basic result in polarization theory.
Oh, there are many.
No. D is of the form. You mean depending on the point I fix? No, but this is equivalent. I mean, the semi-algebraic structure that you put is equivalent under G of R actually, so it does not change. I mean, it's kind of really canonical. This was all the point of the clarification of the appendix we wrote following Christian suggestion. Can I take 5 minutes? Oh, we have 1 hour long break. No, so just to see that there is no magic. Let's do the simplest example so that you understand the definable structure, even in the simplest case where this map is actually algebraic. And you see that even in that case, there is some content there. So let's take the universal, I take a family of elliptic curves. Because there is a moduli space, you can just take the moduli space. So you can, so this is the moduli space of complex elliptic curves. And this is the family of all elliptic curves over it. So this is my situation. So now what is the picture? So I make in that situation exactly the picture I just erased. So what is the universal cover of this? The universal cover, this will parameterize actually elliptic curves plus marking. Plus a canonical identification of H1, but I need space, plus a canonical choice of generator in the cohomology of the elliptic curve. So the elliptic curve is just a 2 torus, so it's dimension 2. And I just choose 2 pairs. It's such an identification. So now what is the peer map? Well, once I have trivialized my local system on this universal cover, I get a peer map that maps me to the peer domain. And so what is this peer domain? This is the union of lower and upper Poincare space. So this is P1C minus P1R. And this is contained inside P1C. So in the previous picture, this guy was D hat, and this guy was D. And this guy is semi-algebraic there. It's open semi-algebraic there. What is the map? Well, the map is just to such an elliptic curve with such a marking. You just do the following thing. You integrate the canonical periods of a gamma 1 of the unique up to scalar holomorphic form on the elliptic curve. And you divide, you take the period. So you divide by what happens over gamma 2. So it gives you some complex number that lies inside here. And what I'm saying is that this is never real. Okay. So this is a complex number that you can interpret as being a point. So this is, if you want, let me write it like this. This is the class generated by this one form inside the dual in this basis. Right. So this is a projective space on those two vectors, on those two on this two-dimensional vector space, and I just write the coordinate of that guy with respect to gamma 1, gamma 2. This is what I'm doing. And now what is, and this map descent, there is an ambiguity because I've fixed this trivialization of the H1. The ambiguity is the choice of Z basis of this Z square. So this goes to this descent to H plus minus modulo GL2Z, which is the same thing as H plus modulo SL2Z. And so, so this is my peer map phi. Yes.
I'm a bit confused because you keep referring to this map as algebraic, but I mean you do not mean
Which one?
The period map.
No, it is not. It is not.
Several times that.
It's never. This guy is never algebraic, except in that case.
Except which
in that case.
What is that?
In the case of elliptic curves, as I said, if you parameterize family of abelian varieties, this guy has an algebraic. This is.
Say it's algebraic because these are definable.
Yes. So the way you have to think about it, you have to separate the structure. Here, I construct the moduli space of elliptic curves abstractly. And what Riemann's theorem is telling you is that if I consider the peer map, which as priori is not algebraic, what happens is that actually in that case, this map is a biholomorphism. And so this means that I can transport the algebraic structure on this. Which...
Yeah, but I mean, in the context where you were speaking, you made a definable structure.
Yes, exactly. So I'm coming to that exactly in 1 second. So I'm assuming that you know an abstract moduli theoretic construction of this moduli space. So it will give you some algebraic structure here. Now what I'm telling you is that I will consider a different definable structure here, and that the theorem is essentially, so I want to put a definable structure here. This is part 1 of the theorem. And part 2 is telling you that for this definable structure, this map is definable. And already this statement is non-trivial because this is not the algebraic structure, the definable structure.
Right.
Exactly. So this is my peer map. And now the remark is that in this super special case, this map is actually a biholomorphism, and the inverse map is what is called the J invariant of an elliptic curve. Okay. So, but now let me explain. So what is the semi-algebraic structure that I want to put here? I explained that you can just take a semi-algebraic structure on the universal cover, which is this very nice guy, and choose a fundamental domain. And the one structure that I would, definable fundamental domain. And the one I would choose is a standard one. We saw the picture yesterday. So you have -1, 1, minus 1.5, 1.5. And this is your fundamental set, which is semi-algebraic here for the action of SL2Z on the upper half space. And I descend this semi-algebraic structure, okay? This is what I'm doing. So this is F semi-algebraic. I could have chosen another one, but I choose that one. So if I want to do that, this is the same picture. There is a general theory that is called reduction theory for arithmetic groups, because as I said, those D mod gamma, D is homogeneous on G of R, and gamma is essentially an arithmetic subgroup there, G of Z. And so this is all contained in reduction theory. Now, what do I want to prove? I want to prove that for the natural definable structure coming from the algebraic structure of this moduli space, this map is definable. Okay. So in this case, showing that phi is definable is the following thing. So now, what I will prove, in fact, is that the inverse is definable. It would be easier in that case. So this is equivalent to showing that J is definable, where now I think of the J function as being a function defined on this fundamental set. Actually, it's defined on full age, and there it is not definable because there is a lot of periodicity, but restricted to the fundamental set. I want to prove that when I map this to the algebraic depth, now you have to believe me that when you do the algebraic construction, what you get here is actually a stack, but the underlying algebraic variety is just C, nothing else. Okay, the affine line. So this guy is just C with its natural algebraic structure, natural Tame structure. So what I want to prove that this thing is definable. Maybe I will just rewrite it here so that space. So I have F, it's like H, and I go to C by J. Okay. So now it's a classical, you study these J invariants, there are formulas for this. So one way of doing it, and we did it much before proving that the general period map is definable, is that you know that this map actually factorizes in the following way. You look at the natural map, which is exponential to pi I. So exactly the same map as what we had in the case of these standard strips. So what it is doing is the x plus iy, and it is mapped by that map to exponential minus this same formula, 2 pi I sinus 2 pi x plus I sinus 2 pi x. And again, this map is definable in R and X because I have this real exponential. Y is varying in this infinite going to infinity, but I don't care. This is definable in Rx. And again, those things are not definable if I'm considering them on full of age, but on the fundamental set where X is bounded between -1/2 and 1/2, it is. So this map is definable in R and X. And now you are reduced to proving that this map is definable in R and X. And now it's a classical fact that actually this map is meromorphic, which means algebraic if I think of this like this. So it's even algebraic there. Okay? So the composite has to be definable. And this is what happens. So you see, even in this super simple case, it's not completely trivial to prove this result. You are really proving that the algebraic structure on the fundamental set, the semi-algebraic structure on the fundamental set is compatible when you extend to Rnx with the natural algebraic structure on S. Okay, so
yeah, I'm confused by why you call this algebraic, because in the natural structure, this is a meromorphic function which is not algebraic, right?
Meromorphic is in one dimension, same thing as algebraic to P1.
Why algebraic?
No, because if you put because you have a single you put the J, because J is like 1/q plus blah blah blah.
Yes.
And
Yes, you have a single pole, but in this cube parameter, you go to P1.
But when you make so when extend it.
It extends. It's a restriction to this guy of this.
Does it mean like what does it mean algebraic?
It means that
But when you use the word algebraic,
yes.
I assume you mean it's algebraic in the canonical definable structure that you define.
No, in the canonical algebraic structure, in the sense delta inside C. So for this parameter Z.
No. But it does extend to C. The map, I don't think the J.
No, it does not. But what I'm saying is that if you want, here this map is meromorphic in the sense that at 0 it's really meromorphic in the natural coordinate. So it's definable in Rn. Yes.
But not in R.
No, not in R. I said R. Sorry. I start being super tired. No, in Rn.
Yeah, just this arrow you say algebraic.
Yeah. I saw algebraic in the sense that there is a single pole, so you get a restriction of a meromorphic map here, and so it's definable in Rn. Sorry. Yeah, sorry.
When you take Humboldt gamma and you say it is a R-alg structure, in some sense you should say that you never use the R-alg.
No, I never used, but I think this is a waste. There is something to be played here. Yes. but okay. Actually, just because, okay, we can discuss this later. So I think I'm super late. I wanted to talk 1 more minute. No, I just want to introduce. So I don't want to give the general idea. You use all the package of the degeneracy of variations of Hodge structure at infinity. You really see that here you are trying to understand what happens to your Hodge structure when you go to the center of that disk. And, okay, so it's a very complicated theory. I had planned to say something, but I just don't have time. Maybe I just want to, Greg, you will introduce Hodge. I don't have to do it? Okay, good. So then I stop here.
Okay,